Deep inside the galaxy cluster, Abell 85, lies a monster, Holmberg 15Ea star, a black hole weighing 40 billion times the mass of our Sun. It is one of the largest ever discovered, and its secrets could change how we understand the universe. In this video, we'll journey into the heart of this cosmic giant. If you enjoy it, please like, subscribe and share, and tell us in the comments, what would you ask if you could peek beyond the event horizon? Thank you for watching. Now, let's begin. Clusters of galaxies rank among the largest bound structures in the cosmos, and Abell 85 is one such congregation where hundreds of systems move within a common well of gravity. Between the galaxies, the space is filled by a hot, rarefied ocean of plasma known as the intracluster medium. Its temperature rises to many tens of millions of degrees high enough that atoms are stripped into free protons and electrons, and this charged gas shines in X-rays. Observatories map its glow and reveal a gently peaked distribution that thickens toward the middle of the cluster. The visible galaxies are only a small fraction of the total mass. Surrounding them is a dark matter halo, whose gravity outweighs the combined stars and gas by a large margin. Although this matter cannot be seen directly, its presence is inferred from the speeds of galaxies, from the shape of the hot gas, and from the overall stability of the cluster over billions of years. The result is a deep potential well in which everything moves from the faintest dwarf to the most luminous central giant. Most member galaxies in Abell 85 are ellipticals or lenticulars. They carry old stellar populations dominated by long-lived yellow and red stars whose formation epochs lie far in the past. Cold gas is scarce. Some of it was heated by repeated shocks in the intracluster medium, and some was removed by tides and by ram pressure as galaxies plunge through the cluster atmosphere. Without a ready supply of cool material, star formation wanes, and the systems take on smooth appearances with little dust and with only mild color gradients. Starlight from these populations adds to the diffuse background known as intracluster light, which forms when stars are tidally stripped and then wander freely within the common halo. Because the cluster is massive, encounters are frequent on cosmic timescales, and each encounter transfers a little energy, gradually changing orbits, and helping to sink the most massive galaxies toward the center through a process called dynamical friction. At the very bottom of that well sits the brightest cluster galaxy, the central giant, that gathers light over an enormous volume of space. In Abell 85, this role belongs to Holmberg 15, which spreads its luminosity across a broad, faint envelope whose outer edges blur into the cluster background. The term brightest in this context does not imply a sharp glare. Rather, it signals a large total light when integrated across a very large area. The surface brightness in the outskirts is so low that careful imaging is required to trace the full extent, and even then the transition from galaxy to cluster is gradual rather than abrupt. In visible light, the central giant appears smooth and nearly featureless, with only gentle twists where tides have tugged and where past mergers have left subtle seams. Dust lanes are not prominent, and there are no spiral arms. The stars in the outer regions drift with mostly random orientations rather than in a single organized spin. The intracluster medium itself shows a central brightening in X-rays, and that peak coincides with the position of the central galaxy. Gas density is highest near the core, and the estimated cooling time there can be shorter than in the outskirts. Left alone, such gas would radiate energy and settle into colder phases. However, gentle forms of feedback act as a thermostat. Even when the nucleus is quiet by quasar standards, weak outflows and the slow inflation of small cavities can stir the plasma and offset cooling. Over long periods, this energy input balances radiative losses, so that the cluster core remains hot and stable. This balance helps explain why the center is not lit by large bursts of star formation, and why the light from the central galaxy remains dominated by old stars. In this environment, minor mergers happen often. Small galaxies on plunging orbits are distorted into streams that wrap around the core. Those streams dissolve and add to the diffuse envelope. Tidal shells and faint arcs mark places where stars pile up briefly before phase mixing erases the pattern. These processes build both the intracluster light and the outer reaches of the central giant, increasing its stellar mass without introducing much new gas. Because the intracluster medium is hot, any gas that is stripped from satellites is quickly heated and does not cool readily to form stars. The result is a calm, smooth optical appearance despite the ongoing assembly. Measurements of galaxy velocities in the cluster indicate a broad spread in speeds that tracks the depth of the potential well. Within the central galaxy, the outer stars exhibit little net rotation, supporting the idea that their orbits were scrambled by repeated interactions, rather than built by a single coherent disk. Holmberg, 15. A star appears in this description as an occasional anchor for the mind, yet the emphasis at this scale remains on the environment that surrounds it. A dark matter halo many times heavier than the sum of all visible components provides the unseen scaffold. A hot plasma, thin yet extensive, fills the spaces between galaxies and responds to pressure and to gentle feedback. An extended low-surface brightness envelope of stars drifts at the bottom of the well, and around it the orbits of lesser members curve under combined gravitational pulls. The center of Abell 85 is thus a place of quiet dominance, where gravity collects matter into a smooth distribution, and where violent episodes are softened by the scale over which they are spread. Even when small disturbances ripple through the intracluster medium, they damp with distance and time, leaving a nearly steady state, in which temperature, density, and pressure vary smoothly. Light from the central giant is the integrated record of this history, faint in its outskirts and brighter toward the center, always blended with the diffuse glow of the surrounding atmosphere. Against this backdrop, the name Holmberg 15 can be used sparingly to keep the narrative tied to a real system, while descriptive phrases such as the central giant, the brightest cluster galaxy, and the cluster anchor convey the same identity in calmer tones. In this view, Abell 85 offers a frame in which the central galaxy rests in a wide basin of gravity, surrounded by a thin, hot atmosphere, watched over by an invisible halo, and accompanied by many smaller companions whose paths are shaped by the whole. The extended envelope of Holmberg 15 stretches outward until its faint surface brightness becomes difficult to separate from the glow of the surrounding cluster. This outer light is the natural continuation of long assembly, where successive mergers have left stars spread across a wide domain. In deep exposures, the galaxy appears less like a distinct island and more like a diffuse haze gently brightening toward the middle. The smoothness is striking. Unlike spirals that show arms or irregulars that carry knots, the outer halo of the central giant shows little substructure. What remains is the integrated light of countless stars, most of them old, arranged in a distribution that falls only slowly with radius. These outskirts illustrate the difficulty of defining where the galaxy ends. Astronomers use profiles of surface brightness measured as the light per unit area across the sky. In smaller ellipticals, the brightness decreases steeply, with radius letting observers identify a limit. In Holmberg 15a, the decline is much shallower, so the outer halo continues far into the cluster background. The faint stars add to the intracluster light, making the galaxy appear even larger when carefully traced. The result is an extended system with a luminosity profile that merges almost seamlessly into the cluster environment. The stars in these outer regions are old. Spectral measurements suggest that they formed billions of years ago with only weak gradients in chemical composition. Such uniformity indicates that their origins were mixed thoroughly by repeated interactions. The outskirts likely contain contributions from many former galaxies torn apart and absorbed. Some stars may have been born in smaller companions before being stripped and captured. Over time, these contributions lost their distinct identities, leaving behind a population that appears homogeneous when averaged together. Velocities measured from the integrated starlight confirm that motions here are mostly random. There is little sign of rotation. Instead, stars orbit in many orientations, some plunging through the center, others looping far out. This isotropy reflects a history where violent relaxation erased ordered structures. The only coherence is statistical velocity dispersions are high, reflecting the deep gravitational well. Even at large distances from the center, stellar speeds remain hundreds of kilometers per second, far faster than orbital speeds in ordinary galaxies. The sheer scale of the envelope is emphasized when compared with the Milky Way. If placed side by side, Holmberg 15, A would extend far beyond the visible disk of our galaxy, yet its surface brightness would appear lower because the light is spread across such a large area. The total luminosity, however, adds up to a dominant value that makes it the brightest cluster galaxy. Its stars collectively outshine any companion not by concentration, but by accumulation. Tidal features appear in careful imaging. Low-contrast shells, arcs, or plumes record the infall of smaller galaxies. These patterns fade with time as orbits mix, but their presence confirms that assembly is ongoing. Each new merger delivers stars to the halo and reshapes the outer light. In some places, the profiles become slightly distorted, showing elongations or asymmetries. Yet the overall impression remains one of smoothness, as though the history of many violent events has been blurred into a calm distribution. Globular clusters also populate these outskirts. As compact swarms of stars, they trace the past accretion of smaller systems. The richest, brightest cluster galaxies often host tens of thousands of such clusters. They extend into the halo and can be used to map the gravitational potential beyond the radius, where diffuse starlight is measurable. In Holmberg 15, a globular clusters act as test particles, confirming the vast reach of the central mass. Their motions echo the same dispersion seen in the field stars, though individual clusters are easier to track. Surrounding this giant are faint satellite galaxies, many so diffuse that they nearly vanish against the background. Their fates are sealed by proximity to the cluster core. Over time, tidal stripping removes stars which are then added to the halo of the central galaxy. Some satellites will be completely disrupted, leaving no core behind. This continual process of accretion explains why the brightest cluster galaxy grows steadily larger, even though star formation inside it is nearly absent. Its growth is not through new birth, but through cannibalism of its neighbors. The transition between galaxy and cluster can also be seen in the way gravitational lensing behaves. In principle, the enormous mass of Holmberg 15A, combined with the dark halo of Abell 85, deflects the paths of background light. Observers use these distortions to measure the distribution of mass. At the outer edges of the central giant lensing signals blend smoothly into those of the larger cluster, reinforcing the impression that no sharp boundary separates them. Instead, one scale merges into another until the whole structure is perceived as a hierarchy of nested wells. In this wide perspective, the ultramassive black hole known as Holmberg 15 star remains hidden. Its influence does not reach the outermost halo directly, yet the galaxy that surrounds it provides the necessary setting. Without the envelope of faint stars and without the repeated mergers that built it, the central mass would not be as extreme. The context of the outer light is therefore crucial. It frames the environment that has enabled one of the largest black holes yet measured to reside in the center. At this distance from the core, the story is still one of faint light, merging with cluster glow of old stars orbiting in random paths, and of long histories blurred into a single smooth distribution. It is a region where boundaries dissolve, where the line between galaxy and cluster is indistinct, and where light declines so gradually that it becomes a challenge to know where the central giant truly ends. Moving inward from the faint outskirts, attention rests on the intermediate radii of Holmberg 15A, where the diffuse halo begins to gather into more concentrated light. At these scales, the profile of brightness shows subtle changes. The decline with distance is no longer as shallow as in the envelope, and the light begins to rise more steeply toward the core. Astronomers measure this change with isophotes, contours of equal brightness drawn across the image. In Holmberg 15A, the isophotes remain nearly circular but display slight variations in ellipticity and orientation. These quiet shifts in geometry reveal a layered history of past accretions and slow relaxation. The stellar populations in this zone remain dominated by ancient stars, yet the gradual gradient of metallicity becomes clearer. Stars closer to the core are on average slightly richer in heavy elements, showing that the densest regions retained enriched gas during early epochs of star formation. The difference is not dramatic, but it hints at a formation sequence where the inner parts experienced more rapid chemical processing, while the outer halo absorbed stars from less enriched systems. Spectral studies across these radii confirm this mild gradient, reinforcing the view of an extended assembly that has smoothed variations over time without erasing them completely. In terms of dynamics, the intermediate regions carry signatures of both past order and subsequent mixing. Velocities measured along the line of sight demonstrate a high dispersion, yet some asymmetries remain. There are traces of anisotropy in the orbital distribution. Some stars favor radial orbits that plunge in and out, while others follow more tangential paths. The balance between these families informs models of how the galaxy formed. Radial motions are often linked to major mergers when galaxies of comparable size collide and scramble stellar trajectories. Tangential biases can arise when cores are scoured by the repeated passage of massive objects. In Holmberg 15, both influences coexist, reflecting a long and complex merger history. Globular clusters in this region provide further clues. They are distributed in two broad groups, a redder, more metal-rich population concentrated toward the center, and a bluer, more metal-poor group that extends farther out. The contrast between them suggests multiple epochs of cluster formation, perhaps tied to different stages of assembly. These compact star swarms orbit within the deep potential, and their radial distribution complements the diffuse starlight. For astronomers, they serve as bright test particles that extend the mapping of gravity into regions where the field stars are too faint for detailed spectroscopy. The smooth appearance of the galaxy masks these dynamical complexities. Photometrically, the intermediate radii display little substructure beyond gentle ellipticity. However, when examined in detail, faint features sometimes appear, low-contrast shells or ripples, where infalling satellites left marks that have not yet fully mixed. Such patterns are fragile and fade with time, but in a few cases they remain visible. They remind observers that even the calmest giant is the product of many collisions. Each intermediate shell or ripple is the ghost of a former galaxy, now dissolved into the whole. The total mass enclosed within these radii is vast. estimates from stellar dynamics indicate values far beyond those of typical elliptical galaxies. The velocity dispersions measured here, often exceeding 300 km per second, require a deep potential well. Dark matter contributes substantially to this mass surrounding the stars with an invisible halo that extends much farther out. The luminous stars serve as traces of this gravity, and their speeds confirm that Holmberg 15A resides at the very center of the cluster's dark halo. The intermediate regions thus act as a bridge between the diffuse outskirts governed by the cluster potential and the denser inner zones increasingly influenced by the black hole at the core. Comparisons with other brightest cluster galaxies highlight the unusual scale of Holmberg 15A. Many central ellipticals show extended halos, but the smoothness and breadth here are particularly pronounced. While some display strong asymmetries or prominent tidal debris, Holmberg 15A shows fewer such interruptions, suggesting either an older, more relaxed state or the smoothing influence of many overlapping mergers. Its profile at intermediate radii follows a declining law consistent with a history of violent relaxation, and yet its sheer size sets it apart. The integrated light in this zone still belongs to billions of stars, each tracing an orbit through the gravitational field. To human eyes, these orbits are invisible, but through spectroscopic shifts, astronomers detect their collective motion. The resulting dispersion is high enough that stars travel across kiloparsec scales in only a few million years. Despite the great distances involved, orbital times are short on cosmic scales. This rapid mixing ensures that any coherent substructure is quickly diluted, leaving the smooth appearance that characterizes the galaxy today. In this perspective, Holmberg 15, it becomes both a unique system and a representative of a class. Its intermediate radii tell of a long history of assembly by mergers, a balance of orbital anisotropies, and the quiet dominance of an unseen dark halo. The light is smoother than the outskirts, yet still faint compared with the core, forming a gentle gradient that guides the eye inward. There is no abrupt boundary, only a continuous deepening of surface brightness and a steady increase in the density of stars. These regions contain the memories of how galaxies grow, written not in discrete structures, but in statistical properties of stars clusters and light profiles. Against this calm, the identity of Holmberg 15. A star remains distant, hidden far inside. The black hole does not govern stellar orbits at these scales, yet the galaxy's central mass and structure are preparing the setting where that dominance will emerge. For now, the view is of an intermediate domain where geometry becomes more regular, gradients become clearer, and stars move at speeds that speak of an immense potential, binding them all together. As the view continues inward, the diffuse glow of the outer halo and the intermediate layers yields to a new feature that sets Holmberg 15. Apart from ordinary elliptical galaxies, the depleted core. Where most galaxies brighten toward the center, this one shows a large region of diminished light, as though stars that once occupied the inner volume have been swept away. The surface brightness profile, measured carefully across radii, reveals a flattening instead of the sharp rise that is expected. This deficit is not a simple observational effect. It persists across wavelengths and has been confirmed with multiple telescopes. The light distribution unmistakably displays a core that is unusually large and faint. Such cores are understood as records of past interactions. When massive galaxies merge, their central black holes sink toward the middle. As pairs or multiples of black holes spiral inward, they eject surrounding stars through repeated gravitational slingshots. The result is a region scoured of stars, leaving a core depleted in light, compared with an extrapolation of the outer profile. In Holmberg 15, This process seems to have operated on a grand scale. The size of the depleted region extends over several kiloparsecs, far larger than in typical ellipticals. This scale signals that not one but several major mergers have taken place, each contributing to the removal of central stars and each increasing the size of the light deficit. Inside the depleted zone, stars that remain move in distinctive orbital families. Box orbits carry them deep into the center before swinging back outward, while other paths skirt tangentially around the hollowed region. These orbits reflect the gravitational history imposed by repeated mergers and by the sinking of massive objects toward the core. Some stars are scattered outward entirely, while others settle into elongated trajectories that avoid the center. The result is a distribution that differs strongly from the steep cusps seen in lower mass ellipticals. The kinematic evidence matches this picture. Spectroscopic studies detect extremely high stellar velocity dispersions in the central regions, values that approach or exceed 350 kilometers per second. Yet despite these speeds, the stellar density remains low, compared with what would be expected if the central profile followed a steep cusp. The combination of high dispersion and low density is precisely what would be produced if large numbers of stars had been expelled by the action of merging black holes. In this sense, the depleted core is both a structural and a dynamical phenomenon, recorded simultaneously in light and in motion. Other brightest cluster galaxies also show cores, but Holmberg 15. A ranks among those with the most extreme examples. Its depleted zone belongs to the rare category of the largest known cores, suggesting a particularly intense history of dry mergers events, where galaxies devoid of gas collide and coalesce without triggering new star formation. Such dry mergers are thought to dominate in dense cluster centers, where gas is scarce and interactions frequent. Each merger not only adds stars to the halo, but also drives the central black holes together, deepening the depletion at the core. The present appearance of Holmberg 15 reflects the cumulative record of these events over billions of years. Beyond its significance for galaxy evolution, the depleted core has direct implications for the central black hole. By measuring the size of the deficit and comparing it with theoretical models, astronomers infer how many black holes have merged there and how much stellar mass has been displaced. The extraordinary scale of the core in Holmberg 15A supports the conclusion that its nucleus houses an ultra-massive object. The stars that remain orbit within a gravitational potential, dominated not by visible matter, but increasingly by the central unseen mass. Photometric models quantify the light deficit by fitting outer brightness profiles and extrapolating inward. The difference between the expected central brightness and the observed flattening yields the missing light, which can be converted into an equivalent stellar mass. In Holmberg 15A, the missing mass reaches values of tens of billions of solar masses, rivaling or exceeding the estimated mass of the central black hole itself. Such comparisons strengthen the interpretation that scouring by black hole binaries is responsible. No other known mechanism can account for both the size of the deficit and the absence of central star formation that might refill it. Even within the depleted zone, faint traces of structure can appear. Some stars remain on eccentric paths that carry them briefly close to the center before flinging them outward again. Others circulate tangentially, avoiding the deepest part of the well. These survivors produce a residual light that gives the core its flat profile rather than a true void. The overall impression is of a hollowed region where density is greatly reduced but not completely absent. This delicate balance testifies to the gravitational dynamics that have shaped it. To observers, the depleted core of Holmberg 15A is not immediately obvious in a single image. Its scale is too large to resemble a small hole, and too faint to stand out dramatically. Instead, it becomes clear through careful analysis of brightness gradients across radii. Only by plotting the light profile and comparing it with standard forms does the magnitude of the deficit reveal itself. Once recognized, however, it is unmistakable, a central flattening where there should be a steep rise, extended over thousands of parsecs, placing this galaxy among the extremes of its class. This hollowed heart is a signpost of past events rather than a static feature. It records the repeated scouring of stars by massive objects spiraling inward, and it sets the stage for understanding how such galaxies grow. In Holmberg 15a, the depleted core is not an incidental detail, but a defining characteristic one that shapes both the appearance of the galaxy and the interpretation of its central mass. As the focus moves gradually inward, the depleted core marks the threshold where the influence of Holmberg 15. A star becomes increasingly significant, guiding the orbits of stars and shaping the very structure of the central regions. Inside the hollowed center of Holmberg 15, where the light deficit has already signaled the removal of stars, the focus turns toward the orbits that remain. The depleted core is not empty. It is a region where stellar density is reduced compared with expectations, but stars continue to move through it on paths that reveal the influence of gravity. These orbits provide clues to the processes that shape the central structure and to the unseen mass that dominates its dynamics. The families of orbits here are diverse. Some stars travel on box-like trajectories that carry them close to the central axis before swinging outward again. Others follow more tangential paths circling around the hollowed region and rarely passing through the very center. The balance between these types is shaped by past interactions. When two massive galaxies merge, their central black holes sink inward and form a binary. This binary ejects stars from the core by gravitational slingshots, removing those on radial orbits most efficiently. The survivors are often those on tangential paths, leaving behind a core that is both depleted in stars and biased in orbital shapes. Measurements of stellar motions confirm this picture. Spectroscopy of the central light shows velocity dispersions that remain extremely high, while indicators of rotation are weak or absent. Instead of coherent spin, the motions are mostly random but with subtle anisotropies that betray the history of selective depletion. The very high dispersions on the order of hundreds of kilometers per second testify to the depth of the potential well. Even though stars are fewer, their speeds remain extreme, governed by both the stellar mass of the central galaxy and the influence of the black hole at the heart. Dynamical models constructed for Holmberg 15. They use these measurements to constrain the orbital distribution by fitting observed line-of-sight velocities with superpositions of orbit families. Astronomers reconstruct the three-dimensional arrangement of stellar paths. Such models reveal that the central core cannot be explained by a simple extension of the outer profile. Instead, it requires the presence of a massive central object, whose gravity dominates within a certain radius. The depleted core and the orbital structures are thus linked directly to the ultramassive black hole. The sheer scale of the core suggests repeated episodes of scouring. Each major merger would have delivered another central black hole, adding to the binary, or even forming a multiple system. As these black holes spiraled inward, their combined effect expelled stars from the center, enlarging the deficit. Over time, the core grew to its present size, among the largest known. The orbital distribution now reflects this cumulative history, a central region dominated not by the presence of stars but by the memory of those that were lost. For the stars that remain, the environment is harsh. Speeds are so high that close encounters are brief and infrequent. The stellar density is too low for new collisions to replenish the center. No gas is available to form new stars in situ because the intracluster medium is too hot to condense. Thus, the depleted core is not only a product of past interactions, but also a stable feature that will persist. Its structure will remain until new mergers bring further changes, either deepening the scouring or altering the orbital mix. The geometry of the core is nearly round, though not perfectly so. Ellipticity measurements show only mild deviations from circularity. This suggests that violent relaxation has smoothed most of the asymmetries that might have arisen from individual events. The light deficit is therefore best described as a broad symmetric feature, lacking the sharp cusps or off-center distortions that could have indicated a single recent disturbance. Such symmetry reinforces the view of a long evolutionary path where many smaller disturbances have been averaged together into a stable state. Globular clusters are sparse in the very center, in contrast with their more numerous distribution at larger radii. This absence is consistent with the scouring scenario. Clusters that ventured too close would have been disrupted or ejected by interactions with the central black holes. Only beyond the depleted zone do their populations recover. Their absence in the inner region provides another indirect sign of the powerful gravitational interactions that have shaped the core. In comparison with ordinary ellipticals, the depleted core of Holmberg 15A is exceptional. Typical cores extend only a fraction of a kiloparsec, but here the scale reaches several kiloparsecs, ranking among the most extreme known. This distinction sets the galaxy apart as a laboratory for studying how repeated mergers influence structure. The size of the core correlates with the mass of the central black hole, and in this case the extraordinary scale points toward an ultramassive object in the tens of billions of solar masses. The orbital structures remain as silent witnesses. Each star on a tangential path, each survivor of the scouring process, represents the residue of a long dynamical history. Their collective light fills the depleted region with a faint glow, not dense enough to restore the cusp, but sufficient to outline the hollow. In their speeds and in their scarcity, they testify to the presence of the unseen mass that governs them all. The depleted core of Holmberg 15. A is thus both a physical structure and a historical record. It marks the place where stars were removed, where orbits were reshaped, and where gravity from merging black holes left a permanent imprint. It is not an artifact of observation, but a genuine feature of the galaxy, confirmed through brightness, profiles, velocity measurements, and comparisons with theoretical expectations. As the view remains fixed on this hollowed zone, the story of repeated encounters and of extraordinary central mass comes into sharper focus, framed by the quiet motions of the stars that still remain within it. Expanded version, deeper inside Holmberg 15. The transition from the hollowed core to the gravitational domain of the central mass becomes unmistakable. Astronomers define this transition by the concept of the sphere of influence, the region where the pull of the black hole is stronger than that of all the surrounding stars combined. For galaxies with black holes of only a few million solar masses, this sphere extends no more than a few parsecs, often too small to resolve at their distances. In Holmberg 15A, however, the extreme scale of the central mass inflates this domain to hundreds of parsecs, a vast proportion of the galaxy's inner body. The sphere of influence is not a physical wall, but a boundary of dominance. Outside it, stellar speeds and dispersions trace the combined potential of luminous matter and dark halo. Inside, the rise in velocity dispersion betrays the added presence of an unseen compact mass. In practice, observers determine this boundary by analyzing the broadening of absorption lines in the integrated light of stars. Spectra collected across the central arc seconds show how the distribution of stellar velocities changes with radius. In Holmberg 15E, the dispersions are already high, exceeding 300 kilometers per second at radii well outside the core. Yet near the nucleus, the broadening grows steeper, requiring the addition of a massive central black hole to reproduce the pattern. The mathematical models used in this analysis are demanding. Observers employ orbit-based dynamical modeling where thousands of possible stellar paths are combined to match the observed kinematics. Each orbit carries different eccentricities, inclinations, and radial extents. By weighting these families, a model can recreate the distribution of observed velocities. Only by including a black hole of tens of billions of solar masses do the models converge with the data. Without it, the predicted dispersions fall short of what is observed within the innermost regions. The sphere of influence is thus not merely theoretical. It is a measured domain reconstructed through the careful fitting of stellar motions. The geometry of this region is nearly spherical, though subtle flattening may persist if the larger galaxy retains anisotropies. Within it, stars move on tighter, faster paths. Some plunge inward on elongated orbits, curving sharply as they swing past the black hole's grip. Others maintain more circular paths, skimming around the unseen center with astonishing speeds. Orbital periods can shrink to only a few million years short by galactic standards. Despite the depletion of stars in the core, those that remain act as natural probes of the gravity that confines them. Their light is faint, but their speeds speak clearly of the immense mass at the center. The rarity of this situation cannot be overstated. In most galaxies, spheres of influence are too compact to resolve beyond the local group. Even in massive ellipticals tens of millions of light-years away, the angular size of the sphere is often less than a fraction of an arc-second. Holmberg 15. A by contrast combines an extreme black hole mass with a relatively favorable distance of a few hundred million light-years. This allows modern observatories equipped with adaptive optics and high-resolution spectroscopy to resolve the inner velocity field directly. The galaxy thus becomes one of the few in which the influence of an ultramassive black hole can be studied at resolved scales. The depleted core itself enhances this opportunity. Because stars are scarce near the center, the light profile is flat, minimizing confusion between the effects of stellar density and black hole gravity. In galaxies with dense cusps, distinguishing between stellar mass and black hole mass is more difficult. In Holmberg 15a, the hollowed profile helps isolate the black hole's contribution. The very absence of stars that signals past mergers now aids astronomers in constraining the central object. Beyond stars, other tracers contribute to mapping the sphere of influence. Planetary nebulae, though faint, can be detected in the halos of some ellipticals and used to measure line-of-sight velocities. In Holmberg 15, a globular clusters at intermediate radii provide additional data points extending the dynamical modeling farther out. Together with stellar absorption lines, they reinforce the conclusion that a compact mass dominates the inner few hundred parsecs. The dynamical timescales inside this sphere are short compared with the age of the galaxy. Stars complete many thousands of orbits over cosmic time, ensuring that any substructures are quickly mixed away. The result is a smooth distribution of velocities lacking coherent rotation or ordered disks. This absence of order is itself informative. It reveals that the system has undergone repeated violent events, with the black hole serving as the anchor around which everything eventually settles. When considering the balance of forces here, one must note the contrast between visible and invisible matter. The light profile is subdued, yet the velocities are extreme. This dissonance is the hallmark of black hole dominance. Mass that cannot be seen still bends, orbit still dictates speeds and still defines the boundary of influence. In Holmberg 15, the scale of this effect is unprecedented, providing one of the clearest windows into the regime of ultramassive black holes. The importance of the sphere of influence extends beyond a single galaxy. By comparing its size and the black hole mass with relations observed in other systems, astronomers test whether scaling laws hold at the extremes. The velocity dispersion of Holmberg-15 are the core size and the inferred black hole mass all lie above the typical ranges, suggesting that the most massive systems may follow different growth paths. The ability to resolve the sphere of influence here offers rare evidence for or against such deviations. In sum, the sphere of influence within Holmberg 15A is not a hidden abstraction, but a real measurable domain where gravity from the central object overpowers all else. It stretches across hundreds of parsecs, shaping stellar orbits, defining velocity dispersions, and confirming that Holmberg-15, a star, is among the largest black holes known. This region stands as the bridge between the observable starlight and the invisible horizon, a zone where evidence is gathered not by sight of the black hole itself, but by the testimony of stars compelled to move under its pull. Once the boundary of the sphere of influence is recognized, the next task is to convert the evidence of stellar motions into a measurement of the black hole's mass. In Holmberg-15A, this work requires detailed stellar dynamical modeling because direct imaging of the black hole is impossible. The method begins with observation spectra collected across the inner galaxy, capturing the absorption lines of thousands of unresolved stars. The broadening of these lines encodes the distribution of stellar velocities along the line of sight. Different positions reveal how this distribution changes with radius, producing a two-dimensional map of velocity dispersions, line shapes, and higher-order moments. To interpret these data, astronomers build dynamical models that include three essential components. The first is the visible distribution of stars derived from the galaxy's light profile and assumed to trace stellar mass when combined with an estimated mass-to-light ratio. The second is the dark matter halo, represented by a parameterized profile that extends beyond the visible galaxy and contributes to the gravitational field. The third is the central black hole, treated as a point mass. The goal is to find the combination of these elements that best reproduces the observed kinematics. The models employ orbit superposition, sometimes called Schwarzschild modeling, after the scientist who introduced the method. Thousands of trial orbits are computed within a trial gravitational potential. Each orbit is assigned a weight, and the weighted sum is adjusted to match both the spatial distribution of light and the velocity data. If the fit is poor, the parameters of the model are altered and the process is repeated. By exploring a large grid of possible parameters, astronomers determine which combination yields the closest match. The result is not a single number, but a range of black hole masses that are consistent with the data and the adopted assumptions. In Holmberg-15, such modelling has consistently pointed to an ultra-massive black hole far above the mass of the central objects in typical galaxies. Early studies suggested values on the order of 40 billion solar masses, though later analyses emphasized uncertainties and provided ranges from tens of billions downward. The differences arise because assumptions about the stellar mass-to-light ratio, the contribution of dark matter, and the treatment of anisotropies can shift the result. Nevertheless, every careful study agrees that the mass is extraordinary, placing Holmberg-15 a star among the most massive black holes measured through stellar dynamics. The uncertainties deserve emphasis. Stellar populations may not follow a constant mass-to-light ratio. Gradients in age or metallicity can alter the relation between light and mass. The distribution of dark matter in the inner regions is not directly observed and must be modelled. Choices of anisotropy in the orbit families can bias the fit toward higher or lower black hole masses. Each of these assumptions introduces systematic uncertainties that are difficult to reduce. For this reason, mass estimates for Holmberg 15 A star are presented as broad ranges rather than exact numbers. The consensus is that the mass lies in the tens of billions of solar masses, with no smaller value able to reproduce the observed dispersions. One strength of the stellar dynamical method is its ability to test consistency. If the central black hole were emitted, the predicted dispersions would flatten at small radii rather than rise, contradicting the data. If the black hole mass were too small, the steep rise in velocity dispersion would not be matched. Only when the black hole mass is large does the model reproduce both the shape and amplitude of the observed kinematics. This provides strong qualitative evidence even when the quantitative range remains wide. The dynamical timescales involved emphasize the stability of the result. Stars inside the sphere of influence orbit so quickly that any transient features would have been mixed away long ago. The present velocity field represents a long-term equilibrium. This makes stellar dynamical modeling reliable for measuring mass because it does not depend on temporary disturbances, but on averaged properties. For Holmberg 15 Se, the equilibrium velocities require a mass that cannot be explained by stars or dark matter alone. Such measurements are challenging in practice. The galaxy lies hundreds of millions of light-years away, so the central region subtends only a few arc-seconds on the sky. Extracting velocity dispersions at these scales requires instruments with both high spatial resolution and high spectral precision. Adaptive optics on large ground-based telescopes combined with integral field spectroscopy provide the necessary data. Space-based observations free of atmospheric distortion also contribute. The fact that the black hole in Holmberg 15A can be studied at all is a testament to advances in instrumentation as much as to the extraordinary scale of the object itself. The results from Holmberg 15A have broader implications. They challenge the upper end of empirical correlations between black hole mass and host galaxy properties. In less massive galaxies, black hole mass scales with the velocity dispersion of stars or with the luminosity of the bulge. Extrapolating these relations to the extreme dispersions of Holmberg 15A predicts black hole masses of only a few billion solar masses, far below the dynamical estimates. This suggests that the most massive galaxies and their black holes may follow different evolutionary tracks shaped by repeated dry mergers rather than by the gas-rich processes that built smaller systems. Although the central mass cannot be seen directly, the consistency of stellar dynamical models across multiple studies makes the case compelling. Holmberg 15. A star joins a small set of ultramassive black holes known through dynamical evidence, providing a critical data point at the upper extreme of the distribution. Its measurement illustrates both the power and the limits of the method precise in tracing relative contributions, but subject to systematic uncertainties that widen the final range. The process of measuring mass dynamically in Holmberg 15A thus represents a balance between data and assumption, between observed velocity dispersions and modelled orbit families. It is a detailed exercise in reconstruction where faint starlight becomes a probe of gravity on scales otherwise inaccessible. The outcome is a portrait of a central object so massive that it reshapes not only the structure of its host galaxy, but also the understanding of black hole growth across cosmic history. From the recognition of a sphere of influence and the dynamical modelling that defines it, the focus turns toward the range of mass estimates that emerge for Holmberg 15 A star. The central object is widely accepted as ultramassive, yet the exact number remains subject to debate. Different groups using different methods have arrived at values spanning from around 10 billion solar masses to more than 40 billion solar masses. The widespread does not reflect uncertainty in the reality of the black hole, but rather the complexity of interpreting data from such an extraordinary system. One source of variation is the assumed stellar mass-to-light ratio. Observers estimate this ratio by modelling the stellar population, its ages, metallicities, and initial mass function. Small differences in these assumptions change the inferred contribution of stars to the total mass, and therefore alter how much mass must be assigned to the black hole. A heavier stellar population reduces the black hole estimate, while a lighter one raises it. For Holmberg 15, the dominance of old stars with subtle gradients adds to the difficulty, since no single ratio applies uniformly across all radii. Another factor is the treatment of dark matter in the models. The inner distribution of dark matter is uncertain. Some models allow for a concentrated profile that contributes significantly even near the center, while others assume a flatter distribution that matters only at larger scales. If dark matter is assumed to contribute strongly in the inner kiloparsecs, the required black hole mass decreases. If its role is minimized, the black hole mass must rise to account for the observed stellar velocities. The truth likely lies between these extremes, but the lack of direct constraints leaves room for systematic differences among studies. Anisotropy in stellar orbits introduces yet another variable. If stars follow more radial orbits, they can produce higher velocity dispersions without as much central mass. If they favor tangential paths, the opposite is true. Dynamical models attempt to reconstruct the mix of orbits, but degeneracies remain. Subtle differences in the assumed distribution lead to different best-fit black hole masses. For Holmberg 15a, the range of orbital structures is wide, so models that weight radial or tangential families differently can produce mass estimates that differ by large factors. Despite these uncertainties, all serious analyses converge on the same conclusion: the black hole is among the most massive ever measured. Even the lowest plausible estimates exceed 10 billion solar masses, placing it well above the central objects of ordinary galaxies. The highest estimates, near 40 billion, suggest an object so massive that it challenges theories of black hole growth. The conservative approach is to present a range in the tens of billions, acknowledging both the strength of the evidence and the limits of current modelling. Comparisons with other brightest cluster galaxies underscore this point. In systems such as NGC 4889 in the Coma cluster, or NGC 1600 in a smaller group environment, dynamical modelling has revealed black holes of more than 10 billion solar masses. Holmberg 15. A sits at the extreme of this distribution, rivaling or exceeding these giants. The consistency across multiple systems strengthens the argument that ultramassive black holes are a natural outcome of repeated dry mergers and central scouring. Yet, Holmberg 15. Air remains exceptional in both the size of its depleted core and the scale of its mass estimate. The reliability of these results depends on the quality of observational data. Spectra must be collected with high signal-to-noise across faint central regions. Integral field units provide two-dimensional velocity fields rather than single long-slit cuts, improving the robustness of models. Adaptive optics sharpen the view, resolving finer structures. Even so, the distance of Holmberg 15a means that uncertainties cannot be entirely eliminated. No single dataset is sufficient. The weight of evidence comes from the agreement of multiple independent observations analyzed with different techniques. There is also the question of alternative methods. Gas dynamical modelling, in which the rotation and turbulence of ionized gas are fitted to infer mass, is not practical here because the galaxy lacks a cold gaseous disk. Masses which provide exquisite dynamical traces in some galaxies are absent in the hot cluster environment. Thus, stellar dynamics remains the only viable path. This exclusivity reinforces the importance of careful modelling and transparent acknowledgement of uncertainties. The presence of such a massive black hole has implications for scaling relations that connect galaxies and their central objects. The black hole mass to stellar velocity dispersion relation, known as the m-sigma relation, predicts values much smaller than those observed here when extrapolated. Similarly, correlations between black hole mass and bulge luminosity fall short. Holmberg 15. A lies above these relations, suggesting that the most massive black holes in the universe may follow different evolutionary rules. Their growth through repeated dry mergers in cluster centers may decouple them from the processes that govern smaller systems. While the numbers vary, the narrative is consistent. Holmberg 15. A star belongs firmly in the ultramassive class with a mass measured in tens of billions of suns. Its gravitational domain shapes not only the orbits of nearby stars, but also the structure of the entire galaxy core. Its existence demonstrates that black hole growth can reach scales far beyond those of quasars in the distant universe. In this sense, the mass estimates, uncertain though they are, point toward a frontier of astrophysics, where extremes challenge established patterns. The discussion of mass ranges is not an abstract exercise. It defines the physical scale of the system, the energy available for feedback, and the role of the black hole in the evolution of its host cluster. Whether the true mass is closer to 20 billion or 40 billion solar masses, it represents one of the largest concentrations of mass in a single object known. The uncertainty does not diminish the significance. Rather, it highlights the frontier of measurement where instruments and models are pushed to their limits. Thus, the mass of Holmberg 15. A star is best described not as a single figure but as a conservative range anchored in the tens of billions. This range captures both the agreement and the caution of current science. It acknowledges the extraordinary nature of the black hole while respecting the uncertainties inherent in modelling such a distant and complex system. In the calm light of the central galaxy, the motions of stars whisper the truth of an unseen mass, whose magnitude defies simple characterization, yet whose presence is beyond doubt. The measurements of mass, though subject to ranges, lead naturally to the question of activity. What does an ultramassive black hole of tens of billions of solar masses actually do in its environment? In Holmberg 15, the answer is subtle. Unlike the blazing quasars of the early universe, which shine with radiation across the spectrum, this black hole is quiescent. Its accretion rate is extremely low. Instead of flooding its surroundings with light, it reveals itself through faint radio emission and the gentle stirring of hot gas in the cluster core. Observations at radio wavelengths detect weak jets or lobes associated with the central galaxy. These are not powerful structures spanning hundreds of thousands of light years as seen in classical radio galaxies, but more modest outflows that indicate the black hole is not entirely dormant. The presence of such emission shows that some gas is indeed being accreted and converted into kinetic energy. The output, however, is small compared with the potential energy available from a black hole of this size. This mismatch suggests that the accretion mode is radiatively inefficient, a state where gas falls inward but releases little light. The environment of Holmberg 15. A supports this interpretation. The intracluster medium is hot with temperatures of tens of millions of degrees. Gas at such high temperatures cannot cool efficiently to feed the black hole at high rates. Instead, material drifts inward, slowly captured by the black hole's gravity, but unable to radiate effectively. This process is often described as advection-dominated accretion, where most of the energy is carried inward with the flow rather than emitted outward. The result is a black hole that grows quietly, releasing only faint radio signs of its activity. Despite its low radiative output, the black hole still influences the cluster environment. Even weak jets can inflate bubbles in the surrounding plasma, redistributing heat and slowing cooling flows. Observations of other clusters show cavities in the X-ray gas where radiolobes have displaced plasma. In Holmberg 15, a similar though smaller effects may occur. This feedback helps maintain the delicate balance that prevents large amounts of gas from condensing into stars. It demonstrates that even a black hole accreting at a low rate can act as a regulator of its environment. The quiet nature of Holmberg 15. A star stands in contrast to its size. One might expect such an enormous object to dominate the sky with luminous outbursts. Instead, it remains nearly invisible in optical light, with only the motions of stars betraying its presence. This duality illustrates the difference between mass and activity. Mass is a permanent attribute recorded in the orbits of stars and the structure of the core. Activity depends on the supply of cold gas, which in the center of a rich cluster is scarce. The black hole may be ultramassive, but it is also starved. X-ray observations of the cluster center add further support. The brightness peak of the hot gas coincides with Holmberg 15. Yet no luminous point source is detected at the nucleus. The absence of such a source confirms that accretion is faint. Instead, the X-ray emission arises from diffuse plasma spread across tens of kiloparsecs. This plasma is dense enough to radiate but too hot to cool rapidly. Without a reservoir of cold gas, the black hole cannot shine as a quasar. Its role is quieter, consisting of low-level heating that offsets cooling in the cluster core. Comparisons with other central galaxies show that this state is common. Many brightest cluster galaxies host black holes that are quiescent or only weakly active despite their enormous masses. The explanation lies in their environments. Gas is heated by shocks and by past activity, preventing the inflow of large amounts of fuel. Holmberg 15. A follows this pattern, but its extreme mass makes the contrast sharper. Here is one of the largest black holes known yet. It glows less brightly than far smaller ones in gas-rich galaxies. The faint activity nonetheless provides valuable information. The detection of radio jets, however weak, proves that the black hole is not completely dormant. By measuring their size and energy, astronomers estimate the mechanical power of the nucleus. These estimates, combined with the properties of the surrounding gas, help quantify the feedback loop that stabilizes the cluster. Even a low-luminosity black hole of tens of billions of solar masses can inject enough energy to influence its environment, showing that scale alone can compensate for low efficiency. The picture that emerges is one of quiet regulation. Holmberg 15. A star does not blaze with quasar light, but it maintains the thermal state of the intracluster medium. It does not dominate observations with bright accretion disks, but it ensures that the central gas does not collapse into a cooling flow. Its presence is hidden in optical light, yet revealed in the absence of uncontrolled star formation. This paradox, an enormous black hole that is almost invisible, illustrates the variety of black hole states across cosmic time. In the present epoch, Holmberg 15, a star exists in balance with its environment. The hot cluster plasma starves it of fuel, and in turn the black hole releases just enough energy to keep that plasma hot. This feedback cycle may persist for billions of years, a stable equilibrium between one of the largest black holes known and the medium that surrounds it. It is an equilibrium defined not by brilliance, but by restraint, a cosmic giant that exerts influence quietly rather than with spectacle. The quiet radioactivity of Holmberg 15, a star, points naturally toward the accretion flow that sustains it. In a conventional active galaxy, accretion involves a disk of cold gas spiraling inward, heating through friction and glowing across the spectrum. In this system, the environment is very different. The central galaxy lies in the dense hot atmosphere of Abell 85, where gas temperatures rise to tens of millions of degrees. Such gas cannot collapse into a thin luminous disk. Instead, it drifts inward, slowly remaining hot as it approaches the black hole. The result is a radiatively inefficient flow, sometimes called advection-dominated, where much of the energy falls into the black hole rather than being radiated outward. This form of accretion explains the mismatch between the mass of Holmberg 15 star and its faint appearance. Even though the gravitational potential could in principle power outbursts brighter than the entire galaxies, the lack of cold gas means the engine runs at only a fraction of its capacity. The fuel that does reach the horizon is hot and tenuous, radiating weakly. What energy is released emerges primarily as mechanical power in jets rather than as radiation. The jets stir the surrounding plasma, inflate small cavities, and offset cooling, but they do not produce the luminous beacons that quasars display. The balance between inflow and feedback defines the state of the cluster core. Gas drifts inward under gravity, but as it approaches the center, it encounters turbulence and shock waves driven by the black hole's weak outflows. These processes deposit heat into the plasma, raising its temperature and slowing further infall. In this way, the black hole acts as a thermostat regulating the supply of its own fuel. The rate of growth remains extremely low, so that even over billions of years the black hole's mass increases only modestly compared with its existing scale. This steady balance is supported by X-ray observations. The hot plasma near the center shows signs of heating that cannot be explained by cooling alone. Small cavities and ripples in the brightness map suggest that past outflows have disturbed the gas. These structures are faint compared with the dramatic bubbles seen in clusters like Perseus, but they are consistent with low-level feedback from Holmberg 15 star. The scale of the central mass ensures that even weak activity has significant influence, because its gravitational reach holds so much gas within range. At smaller radii, the flow of gas becomes more speculative. Observers cannot directly see material within a few parsecs, but models predict that the hot plasma transitions into a two-temperature regime as it approaches the black hole. Electrons and ions decouple with most of the energy locked into ions that carry it across the horizon without radiating. This deep inefficiency explains why even one of the most massive black holes in the universe can appear nearly invisible. The horizon swallows matter silently without the brilliant accretion disk that typifies younger or more gas-rich systems. The contrast with quasars in the early universe is striking. Their black holes of only a few billion solar masses produced light visible across cosmic distances. In Holmberg 15a, the mass is greater by an order of magnitude, yet the light is nearly absent. The difference is fuel supply. In the young universe, gas was abundant and cold, feeding black holes at rates close to their maximum capacity. In the present epoch, central cluster galaxies are starved, surrounded by hot plasma that cannot condense. The black hole remains as massive as any in history, but its growth and radiation are stifled. Even so, the dynamics of inflow can be traced indirectly. The faint radio jets are evidence that some of the gas forms a rotating structure before reaching the horizon. Magnetic fields within this structure channel energy, outward launching streams that carry momentum far into the intracluster medium. The efficiency of this process is low, but the absolute scale of the black hole ensures that the mechanical energy remains significant. Thus, Holmberg 15. A star participates in the cycle of cluster regulation, not through brilliance, but through persistence. The quiet accretion flow also influences how astronomers model the black hole's growth history. With present-day rates so low, most of its mass must have been assembled in the past, likely during epochs of more frequent mergers when gas was still available. Today the flow is a faint echo of those active periods, a residual trickle that maintains but does not transform the central mass. By studying it, astronomers learn not only about the current state of the black hole, but also about the transition from quasar epochs to the quiet giants that dominate cluster centers now. In summary, the accretion flow around Holmberg 15, a star, is characterized by inefficiency and restraint. Hot gas drifts inward, releasing little light, while weak jets provide the main channel of energy output. The black hole grows slowly, its vast mass maintained rather than rapidly increased. The environment remains in equilibrium, hot plasma kept from cooling catastrophically, a cluster core stabilized by a regulator too faint to see directly. This is the signature of an ultramassive black hole in the modern universe, quiet yet powerful, invisible yet central to the structure that surrounds it, having followed the quiet accretion flow that feeds Holmberg 15. A star, the natural step is to consider the scales near the event horizon itself. Though invisible directly at this distance, the properties of a black hole of tens of billions of solar masses can be described through well-understood physical relations. The defining boundary is the event horizon, the radius within which not even light can escape. For an object of this mass, that radius is vast compared with black holes in ordinary galaxies. Expressed in terms of distance, it spans a size comparable to the orbit of Neptune around the Sun, yet compact relative to the galaxy that hosts it. The Schwarzschild radius, as it is called for a non-rotating case, scales directly with mass. For Holmberg 15, a star, this distance is measured in hundreds of billions of kilometers. To put it in perspective without resorting to numerical shorthand, the horizon would enclose a sphere tens of light-hours across. Though this is minuscule compared with the galaxy, it dwarfs the corresponding horizon of the black hole at the Milky Way's center. Sagittarius, a star with its mass of a few million suns, has a horizon only about the size of Earth's orbit. Holmberg 15. A star is larger by many orders of magnitude. The timescales associated with such a black hole are equally extreme. The orbital period at the innermost stable circular orbit, where matter can circle the black hole just before plunging inward, lasts many days rather than minutes. Around stellar mass black holes, these orbits complete in milliseconds. Around supermassive black holes, they may take hours. In Holmberg 15, a star, the immense scale, stretches these cycles to macroscopic lengths of time, demonstrating how size alone alters the physics of the near-horizon region. The density implied by such a mass within such a radius remains astonishing. Although the average density decreases with increasing mass, the compactness is absolute. All tens of billions of solar masses are confined inside a boundary, only light-hours across. The curvature of space-time is gentle at the horizon, compared with smaller black holes, yet the escape velocity still reaches the speed of light. This distinction illustrates a subtlety. Ultramassive black holes are less dense on average, but no less absolute in their grip on light and matter. Accretion flows approaching the horizon encounter unique conditions. In standard models, the gas becomes optically thin, meaning photons can escape easily, but because of the inefficiency of the flow, few photons are produced. Magnetic fields become crucial, channeling angular momentum and launching jets. In Holmberg 15, a star, the low inflow rate means that the horizon is not surrounded by a brilliant accretion disk. Instead, material drifts inward, quietly heated to extreme temperatures yet radiating little. The photons that are emitted escape quickly, carrying away only a fraction of the available energy. If the black hole spins, the innermost orbits shrink, and the potential for jet power grows. The precise spin of Holmberg 15. A star is unknown, but its weak radioactivity suggests that some rotational energy may be tapped to launch jets. In principle, the spin of such an ultramassive black hole could store an energy reservoir rivaling the total output of all stars in its host galaxy over billions of years. Whether that reservoir is used depends on the accretion state. In this case, the evidence points to only modest tapping of that energy. The horizon itself remains hidden forever from view. Even the most powerful observatories cannot resolve it at this distance. For comparison, the Event Horizon Telescope succeeded in imaging the shadow of M87, a black hole of several billion solar masses located tens of millions of light-years away. Holmberg 15 lies much farther, and although its horizon is larger, the angular size on the sky is smaller. Direct imaging of its shadow is therefore not feasible with current technology. Its existence is inferred entirely from dynamics, not from silhouette. Nevertheless, by calculating the scale of the horizon, astronomers gain a sense of proportion. The black hole is a gravitational anchor whose boundary would enclose entire planetary systems. Yet from our vantage point it is a point-like nucleus contributing nothing to the visible image of the galaxy. Its presence is betrayed only by the high speeds of surrounding stars and the faint whisper of radio emission. This contrast between immensity and invisibility captures the paradox of ultramassive black holes. They are at once among the largest structures defined by gravity and among the most elusive in direct appearance. The event horizon is also the limit for causal contact. Anything crossing inward is lost from the universe outside. In Holmberg 15, this means that hot plasma drawn from the intracluster medium once past the horizon no longer contributes to observable emission. The material's energy is added to the mass of the black hole, increasing it imperceptibly over long spans of time. At current accretion rates, the growth is negligible compared with the total mass, yet it continues nonetheless, a steady accumulation of matter into the unseen core. This inner scale completes the journey from the diffuse outskirts of the galaxy to the very boundary of space and time defined by Holmberg 15. A star. Each step inward has revealed a different regime, the cluster environment, the outer halo of stars, the depleted core, the sphere of influence, the accretion flow, and finally the event horizon. At this ultimate boundary, the details of orbits and dispersions give way to the absolute physics of a horizon that no light can cross. It is a domain described only by mass spin and charge, stripped of all other details by the nature of black holes. The immense horizon of Holmberg 15. A star defines one scale, but the formation of such a colossal object raises another question. How did it reach this mass over cosmic history? Black holes of stellar origin begin with only a few solar masses. Even those born in the earliest galaxies fed by abundant gas rarely exceed a few 100,000 solar masses in their first growth stages. To reach tens of billions requires processes that operate over billions of years. In the dense centers of galaxy clusters, the dominant mechanisms are thought to be dry mergers and core scouring. Dry mergers refer to the collisions of galaxies largely devoid of gas. In the early universe, when galaxies were gas-rich, mergers triggered intense star formation and luminous accretion onto black holes. In the later epochs of cluster evolution, however, most galaxies lost their cold gas to heating and stripping by the intracluster medium. When such galaxies merge, they add stars and black holes but little fresh fuel. The result is growth in mass without bursts of new star formation. In Holmberg 15a, The diffuse outer halo and enormous stellar envelope testify to countless such dry mergers. Each brought in stars and, crucially, another central black hole. When two massive black holes sink toward the center of a newly merged galaxy, they form a binary system. This pair ejects stars from the core through gravitational slingshots, producing the depleted profiles observed in brightest cluster galaxies. Over time, dynamical friction and interactions with surrounding stars shrink the binary orbit until gravitational waves carry away the remaining energy, merging the pair into a single larger black hole. Repeated many times over the lifetime of the cluster, this process builds an ultra-massive object. The hollowed core of Holmberg 15 is consistent with such repeated scouring. The sheer scale of the deficit implies not one but several major black hole mergers. This picture is reinforced by comparisons across clusters. Brightest cluster galaxies often show large cores and elevated black hole masses, suggesting a common evolutionary track. Yet Holmberg 15 stands out. Its core is among the largest known and its mass estimates exceed most others. This extremity likely reflects the particularly rich merger history of Able 85. The cluster contains hundreds of galaxies, providing ample opportunities for infall and coalescence. Over billions of years, the central galaxy has acted as a collector, absorbing companions and accumulating their central black holes. The evidence for such a history is visible in the structure of the galaxy. The faint shells and tidal features in the outer halo record past mergers. The broad diffuse envelope demonstrates repeated accretion of stars stripped from smaller systems. The smoothness of the intermediate radii shows that violent relaxation has erased individual signatures, blending them into a single luminous profile. At the very center, the depleted core testifies to the scouring action of binary black holes. Each structural layer tells part of the story of assembly, culminating in the ultramassive object now hidden at the heart. Another line of reasoning supports this growth channel. The timescale for gas accretion is limited by the scarcity of cold material in cluster centers. Even if the black hole were to accrete continuously at high efficiency, it would struggle to reach tens of billions of solar masses within the age of the universe. Mergers of black holes, however, can rapidly increase mass without the need for abundant fuel. Each merger adds mass directly bypassing the inefficiencies of radiatively quiet accretion. For a central galaxy like Holmberg 15, located in a crowded cluster core, such mergers are not rare events but expected outcomes. The connection between core size and black hole mass has been explored across many galaxies. Larger cores correlate with higher inferred masses consistent with the scouring mechanism. Holmberg 15 sits at the upper extreme of this relation. Its depleted core, extending several kiloparsecs, matches the expectation for repeated mergers involving ultra-massive black holes. In this sense, the galaxy is not an anomaly, but the natural endpoint of the same process that operates at smaller scales. It represents what happens when dry mergers are repeated enough times in a dense cluster environment. Yet questions remain. The exact sequence of mergers, the times at which they occurred, and the relative contributions of gas accretion versus black hole coalescence cannot be reconstructed in detail. Simulations reproduce similar structures when multiple dry mergers are imposed, but the specific history of Holmberg 15A is lost in time. What remains are structural clues: the smooth outer envelope, the faint tidal debris, the globular cluster system, the depleted core, and the extraordinary black hole mass. Together, these clues point toward a long and violent past smoothed by relaxation into the calm appearance seen today. The implication of this history reaches beyond a single galaxy. It suggests that ultramassive black holes may be the inevitable outcome of central growth in rich clusters. If so, then systems like Holmberg 15A are not isolated curiosities, but representatives of a class of objects that mark the endpoints of galaxy evolution. They are rare because only the most massive clusters provide the necessary environment, but within those environments they may be common. Each one stands as a record of billions of years of mergers, accretions and scouring. Holmberg 15A, with its vast halo, enormous depleted core and ultramassive black hole, offers perhaps the clearest example. Its present quiet state belies the violence of its past. The giant at its centre grew not in isolation but through repeated encounters, absorbing companions and merging their central engines into one. The result is an object that tests the limits of black hole formation theories and provides a living record of cluster-driven growth, the ultramassive scale of Holmberg 15. A star naturally raises questions about its broader context in the universe. Black holes of such magnitude are rare, and their study provides a window into the limits of cosmic structure formation. To place this object in perspective, astronomers compare it to other known extremes. In M87, the central black hole reaches several billion solar masses. In NGC 4889 in the Coma cluster, the central black hole may approach 20 billion solar masses. In NGC 1600, a galaxy in a small group estimates also reach more than 10 billion. Yet Holmberg 15A, with mass ranges in the tens of billions, and possibly above 40 billion, pushes beyond these examples. It stands near the theoretical edge of how large black holes can become within the age of the universe. Such scale prompts examination of scaling relations. For smaller galaxies, the mass of the black hole correlates tightly with the velocity dispersion of the stellar bulge and with the overall stellar mass. These relations underpin much of modern understanding of galaxy black hole coevolution. But at the ultramassive end, Holmberg 15, a star lies above the expected values. Its black hole is heavier than predicted by its velocity, dispersion and luminosity. This suggests that the processes driving growth in central cluster galaxies differ from those that shaped ordinary systems. Dry mergers and black hole coalescences may allow central masses to outpace the stellar populations around them, breaking the linearity of scaling laws. The rarity of such objects also carries implications for cosmology. If ultramassive black holes are common in cluster centers, they contribute a small but significant fraction to the overall mass density in black holes across the universe. Their feedback may influence the thermal state of intracluster gas regulating star formation, not only in the brightest cluster galaxy, but also in satellites. In this way, Holmberg 15, a star is not just a curiosity but a driver of its environment on scales of hundreds of kiloparsecs. Even low-level jets and outflows powered by such a mass can inject enough energy to balance cooling in the cluster core. The quiet state of Holmberg 15, a star, today belies the possibility that it was once far more active. In earlier epochs, when mergers delivered not only stars and black holes but also gas, the nucleus may have shone as a quasar. If so, it would have been visible across billions of light-years, rivaling the brightest objects in the universe. Today the fuel is gone and only the remnant mass remains silently anchoring the cluster. The contrast between past and present reminds astronomers that activity is transient while mass is permanent. The light has faded, but the gravity endures. Simulations of cluster formation provide theoretical support for this narrative. When many massive galaxies merge in a dense environment, their central black holes sink and coalesce, producing remnants of increasing mass. Over cosmic time, these remnants accumulate into ultramassive objects. The larger the cluster, the more mergers occur and the more massive the central black hole becomes. Holmberg 15. A residing in the rich environment of Abell 85 exemplifies the outcome of this cumulative process. Its depleted core, its extended halo, and its ultramassive nucleus all align with predictions of hierarchical growth. Yet the question of ultimate limits remains open. Could black holes exceed even the scale of Holmberg 15? A star, theoretically, growth is constrained by both cosmic time and the availability of material. At tens of billions of solar masses, accretion slows because mergers are less frequent and fuel is scarce. Gravitational wave recoil during black hole mergers may also eject remnants capping growth. Observationally, few candidates exceed the mass range inferred here. This suggests that Holmberg 15, a star, lies close to the natural ceiling, an endpoint of black hole evolution in the current epoch. The presence of such an endpoint has consequences for our understanding of galaxy clusters. It implies that brightest cluster galaxies are not just the largest stellar systems, but also the sites of the largest black holes. These objects embody the convergence of cosmic processes: galaxy merging, dark matter, assembly, hot gas dynamics, and black hole growth. Holmberg 15 demonstrates how these processes can combine to produce extremes that defy extrapolation from smaller scales. On the observational side, Holmberg 15a remains a target for future instruments. The next generation of extremely large telescopes with mirrors 30 to 40 meters in diameter will resolve its central kinematics with greater precision. Improved measurements will refine the mass-range test models of orbital anisotropy and reduce systematic uncertainties. Space-based observatories in the X-ray and radio domains will map the feedback structures with higher resolution, clarifying how even faint jets affect the intracluster medium. Though the black hole cannot be imaged directly like M87, the indirect evidence will continue to sharpen. Holmberg 15, a star, therefore serves as both an anchor and a frontier. It anchors scaling relations by defining their upper extreme, and it marks the frontier of observation, where instruments are stretched to measure objects at the very edge of possibility. It is quiet yet immense, invisible yet defining. In its center light is absent, but the weight of tens of billions of suns is compressed into a horizon only light hours across. For the surrounding cluster, it is the gravitational focus, the regulator of gas, and the record of a violent past now smoothed into calm. The recognition that Holmberg 15, a star, may lie close to the upper limit of black hole growth naturally directs attention to its role within Abell 85. Central galaxies and clusters are not isolated objects but nodes through which much of the cluster's evolution flows. The ultramassive black hole at the core does not simply sit in silence. Even in its quiet state, it acts as a stabilizing influence on the cluster atmosphere. By heating the hot plasma just enough to prevent catastrophic cooling, it governs the fate of gas that would otherwise form stars in the central galaxy. The regulation of star formation in brightest cluster galaxies is a long-standing puzzle. In many clusters, X-ray data suggest that cooling times in the core should be short, yet observed star formation rates are low. The resolution of this discrepancy lies in feedback from central black holes. Even weak jets and outflows repeated over billions of years deposit enough energy to counterbalance radiative cooling. In Holmberg 15, the modest radioactivity and the absence of large star-forming regions fit this model. The black hole grows slowly, the galaxy remains quiescent, and the cluster core retains its hot diffuse state. This equilibrium highlights the difference between Holmberg 15a today and its probable past. Billions of years ago, when mergers delivered gas as well as stars and black holes, the nucleus may have undergone quasar phases. During those times, feedback would have been stronger, carving out cavities and enriching the intracluster medium with metals. Now, with fuel largely exhausted, the balance persists at lower power. The historical record is written not in current luminosity, but in the metallicity of the surrounding gas and the structure of the depleted core. The impact of Holmberg 15. A star also extends beyond energy regulation. Its gravitational dominance at the cluster center influences the orbits of satellites and the distribution of intracluster light. The stars stripped from merging galaxies are not scattered randomly, but are collected into the diffuse halo of the central giant. In this way, the black hole indirectly shapes the cluster's visible structure, even though it does not act on individual stars at large radii. The concentration of mass at the center provides the anchor around which the cluster's architecture stabilizes. Globular cluster systems around Holmberg 15A also reflect this central influence. Their orbits extend far into the cluster, serving as traces of the gravitational potential. Observations show thousands of such clusters, both metal-rich and metal-poor, distributed across vast distances. Their dynamics confirm that the mass of the central galaxy dominated by the ultramassive black hole, and its halo dictates motions far outside the visible core. These clusters carry the imprint of both the galaxy's history and its present gravitational field. The presence of Holmberg 15. A star is therefore not only a fact about a single galaxy, but about an entire cluster ecosystem. Without its stabilizing feedback, cooling gas could condense into stars, transforming the appearance of the brightest cluster galaxy. Without its gravitational anchor, the orbits of satellites would shift, altering the density profile of the cluster core. Its role is thus central in both a literal and functional sense. It sits at the nadir of the gravitational well and maintains the equilibrium of matter and energy around it. The broader cosmological implications also come into view. Ultramassive black holes like Holmberg 15. A star serve as laboratories for testing the physics of feedback and the extremes of black hole growth. They help define the boundary conditions for models of structure formation. If feedback from such objects can regulate hot gas over billions of years, then simulations of clusters must include this process to reproduce observed properties. If black hole masses can exceed the predictions of scaling relations, then those relations must be revised for the most massive systems. In this way, the study of one extreme object informs the understanding of the universe at large. Despite its importance, Holmberg 15, A remains faint in ordinary light. To the eye, it is only a smooth elliptical glow at the cluster center. No brilliant quasar reveals the central engine, no spectacular jets dominate the radio sky. Its significance lies in quiet dominance, not dramatic display. The ultramassive black hole shapes its galaxy and cluster through long-term stability rather than momentary spectacle. This contrast underscores the diversity of black holes. Some are seen through outbursts and flares, others only through the calm order they impose on their surroundings. In the story of Holmberg 15, a star, the present is one of balance, the past one of mergers, and the future one of continued quiet regulation. Its mass ensures permanence, its activity ensures equilibrium, and its place at the cluster center ensures influence. As long as the hot plasma remains stable and the supply of cold gas remains scarce, the black hole will remain quiescent, its presence inferred rather than seen. For astronomers, that inference is enough to establish its role as one of the most massive and consequential black holes yet measured. The portrait of Holmberg 15. A star would not be complete without considering the open questions that extend beyond current measurements. Astronomers have traced its outlines through the depleted core, the high-velocity dispersions, and the dynamical modeling that points toward a black hole mass in the tens of billions of suns. Yet the uncertainties remain large, not because the evidence is weak, but because the system itself lies at the very frontier of what can be studied with present technology. In this way, Holmberg 15. A star is both a data point and a challenge, a reminder of how far observation has come and of how much farther it must go to probe extremes like this. The depleted core among the largest known raises a fundamental question about the sequence of events that created it. Did a few exceptionally massive mergers carve out this hollow in a handful of violent episodes, or did many smaller encounters accumulate their effects over longer timescales? Each possibility leaves a different imprint on the orbital structure of the stars that remain. Detailed mapping of anisotropies could in principle distinguish between them, but current data only reveal the broad outcome: a central region scoured of stars on radial paths, leaving tangential orbits dominant. This leaves open the deeper reconstruction of how exactly the hollowed light profile came to be. The black hole itself, though measured indirectly, is surrounded by questions about its spin and orientation. Spin affects both the efficiency of accretion and the potential to launch jets. If Holmberg 15, a star spins rapidly, then its rotational energy represents a reservoir larger than the total output of all the stars in its host galaxy. Yet the faint radio emission suggests that only a fraction of this potential is being tapped. Whether this reflects a slowly spinning hole or simply an absence of gas to channel the spin energy remains unresolved. Future facilities may probe the jets in more detail, but for now the spin of the ultramassive object is an unknown hidden beneath layers of inference. The cosmic history of this system is likewise incomplete. If Holmberg 15, a star, truly exceeds 20 or even 40 billion solar masses, then much of that growth must have occurred in the early universe when gas-rich mergers were more common. During those epochs, it may have appeared as a blazing quasar shaping its environment with intense winds and radiation. Today, no such brilliance remains, only the silent weight of the remnant. Linking the quiet present to the luminous past requires simulations and indirect clues. The metallicity of the intracluster medium, the faint relics of tidal debris, and the smoothness of the halo all serve as pieces of evidence, but the full chronology cannot be observed directly. Beyond the history of growth, there is the question of how long such equilibrium can last. The cluster environment provides stability with hot plasma and weak feedback maintaining balance. Yet future mergers could disrupt this calm. If another massive galaxy falls into Abell 85 and delivers its central black hole to Holmberg 15A, a new binary will form, reigniting the cycle of scouring and gravitational wave emission. Over cosmic timescales, such encounters remain possible, though at lower frequency now than in earlier epochs. The present state of balance is therefore not necessarily permanent. Holmberg 15, a star, also has significance for the future of gravitational wave astronomy. Pulsar timing arrays sensitive to the very low frequencies expected from binaries of ultramassive black holes may one day detect signals from systems like it. If repeated mergers built this giant, then its history is written not only in light, but in waves that ripple across space-time. Though these events are long past the detection of similar binaries in other galaxies, would confirm the pathway suggested here. Holmberg 15. A star thus sits not only at the frontier of black hole demographics, but also at the edge of a new observational era. For all its extremes, the galaxy remains faint and smooth in visible light. Its halo is diffuse, its center flat, its nucleus quiet. Only with careful spectroscopy and high-resolution modeling does the hidden mass reveal itself. This contrast between appearance and reality underscores the importance of indirect evidence in astrophysics. The stars serve as messengers, their high dispersions carrying the imprint of the unseen. The depleted core serves as a scar recording the passage of black holes now long merged. The faint jets serve as whispers revealing that accretion, though weak, continues. Together, these clues construct the case for one of the largest black holes known, even though no light from the object itself is seen. The future of studying Holmberg 15A will depend on the next generation of instruments. Extremely large telescopes will resolve its central kinematics in greater detail, narrowing the mass range and testing models of orbital structure. Space observatories will map the hot plasma with higher precision, tracing the influence of feedback. Radio arrays will measure the faint jets with greater sensitivity, clarifying the mechanics of low-level activity. Each of these steps will refine the picture, but none will diminish the basic fact at the heart of Holmberg 15. A lies an ultramassive black hole that defines the extreme edge of cosmic growth, thus the story of Holmberg 15. A star is not one of final answers but of continuing questions. It is a case that pushes methods to their limits and challenges theories to accommodate its scale. It demonstrates that the universe can produce objects far beyond the range first imagined, and it stands as a reminder that even the quietest galaxies may conceal histories of immense violence. In its calm present Holmberg 15, A is an anchor of stability in a Bell 85, but within its hollowed center resides a mass that reshaped its galaxy, altered its cluster, and continues to define the boundary of what is possible for black holes.